Welcome back everyone. In this lecture, whatever properties that we have actually postponed in the last lecture about simple roots, I will prove now. Okay. So, these basic properties are going to play a vital role later. So, let us prove them. Actually, they are very important in order to understand the set of roots. Okay, so let me call it as lemmas. So, here is the lemma A. So, what it says? So, if we start with a positive root which is not simple, then you will be able to subtract some simple root from that root, which is so that it remains positive. Okay. If alpha coming from phi. So, let us fix this simple roots pi inside phi. So, this is set of simple roots or bases. Okay. So, now everything related to this pi. If alpha is in phi and assume that alpha is not in pi. So, this is not simple. So, then there exists beta, okay. There exists beta which is from pi such that this alpha minus beta, this is actually a root. So, if we assume alpha is positive, then we can make sure that this alpha minus beta is also a positive. Okay. So, how one does this? Recall from our earlier discussion. So, we observed that if you take elements of pi, so they are all, they make obtuse angle between them. Okay. So, any two elements, if alpha beta is in, okay, let us say alpha dash beta dash is in pi. So, then beta dash alpha dash must be less than or equal to 0 unless alpha dash is not equal to beta dash. So, this is what we observed. We also observed one more thing. So, let me recall here. If we have pi set of roots, okay. So, this is just even a subset of E, okay. This is just a finite subset, let us say. So, this is a finite subset of E such that let us say you label it as alpha 1 etcetera alpha L. So, if alpha I alpha j, so this inner product is less than or equal to 0 whenever I not equal to j, and there exists gamma inside E such that these alpha i's lie on the one side of the gamma for all 1 to L. So, then these data will force that pi is linearly independent. Okay. So, this is something we already proved. Okay. So, this is actually nature of a base. Okay. That is why this, if we take this pi of gamma, we proved that the pi of gamma satisfies all these conditions. So, in particularly pi of gamma becomes a base. So, now for any finite subset that makes obtuse angle between the roots, between the elements, okay, and then stays on one side of the hyperplane defined by some gamma. So, then that must be linearly independent, that is what it says. Okay. So, now in particularly if we take this alpha, okay, here is the proof. If we assume this alpha with inner product with beta is less than or equal to 0 for all beta inside pi. So, then what happens? So, you can identify pi with pi of gamma. Okay. So, there is a regular element gamma such that pi equal to pi of gamma, in particularly phi plus will become equal to phi plus of gamma. Okay. So, then what happens? So, that means this alpha gamma is positive and we also have beta alpha is less than or equal to 0 for all beta in pi. So, now using this observation that we have on the side here, we can see that this pi union alpha, this becomes linearly independent. This becomes linearly independent. So, that is absurd because pi is the base already of your E. So, that is the contradiction. So, that contradiction forces that this there exists beta inside pi such that this alpha beta must be positive. Okay. If alpha beta is positive, then using the lemma that we had earlier, you can immediately conclude that beta minus alpha, sorry, alpha minus beta. So, both are root actually, alpha minus beta, that is what we want. So, this is a root again. Okay. So, now you write alpha as summation k gamma, gamma where gamma coming from pi. So, now if you subtract, you can see that these k gammas are all non-negative integers, okay. And you can also see that this k gamma must be positive for some gamma not equal to beta. Otherwise, what will happen? Alpha will become multiple of beta. Okay. So, k gamma is non-negative integer for all gamma in pi, and there exists gamma inside pi such that this k gamma must be positive and this gamma must be not equal to beta. So, why such k gamma exist? Otherwise, what will happen? This k gamma will be 0 for all gamma not equal to beta. So, then that will force alpha is multiple of k beta. So, that is multiple of beta. So, that is absurd. So, that forces this is true. In particularly, if you take alpha minus beta, you can see that this is nothing but in particularly this k gamma dash where gamma dash in pi minus beta will be there. So, then this k gamma minus beta. So, this part will still survive inside the summation. Okay. So, that makes it this alpha minus beta is actually again positive as k gamma inside alpha minus beta is still positive integer. Okay. So, that proves that this alpha minus beta is positive again, that forces that all coefficients of this alpha minus beta is positive. So, that means alpha minus beta is again positive. Okay. So, as a corollary, you can immediately see that if I start with any beta inside p plus, then this beta can be written as some alpha 1 plus etcetera some alpha t, where this alpha is comes from pi in such a way that if you take any partial sum, each partial sum alpha 1 plus etcetera plus alpha I, this will be again positive root. Okay. So, this is something you can prove using induction and earlier lemma. So, use induction on the height of beta and the lemma that we proved earlier. So, this lemma A. Okay. So, using this you can complete the proof, I am not going to do it. So, now this is something very interesting observation, this corollary. I will tell you like what will be the Lie algebra like input for this corollary. So, basically we seen that if we take this semi simple Lie algebra corresponding to this root system phi. So, this is generated by G alpha where alpha coming from phi. So, this is what we proved, okay, because if you recall G is actually H direct sum G alpha, alpha comes from phi, this is what we had. So, then it is not hard to see H is actually sub algebra of this sub algebra generated by G alpha and phi, that forces G equal to G alpha. But indeed later we will prove. So, later we will prove that G must be actually equal to G alpha where alpha comes from pi. So, only the simple roots are good enough to. So, root spaces corresponds to simple roots, they are good enough to actually generate this entire G. So, that is what we will prove later. So, in particularly G beta for each beta. So, let us take beta to be just comes from phi plus. So, then the G beta will be subspace of this G alpha alpha generated by pi. Since these are all one dimensional spaces, you can see that this x beta that comes from G beta. So, that must be exactly equal to the Lie product generated by this G alpha. So, indeed what one can prove, so this is something one can use Jacobi identity and then prove. So, use Jacobi identity and prove that this x beta can be written as x alpha 1 bracket etcetera bracket x alpha 2 bracket x alpha t minus 1 comma x alpha t, where these x alpha i's will come from G alpha I, where alpha I will come from pi. Okay. So, this is some particular way of getting these Lie words. So, these are called right normed Lie words. So, once we know that G alpha generate alpha in pi, then it is immediate that x alpha will generate when alpha coming from pi. So, in particularly, okay, sorry, we have to use both x alpha as well as minus alpha. So, what I said is wrong. So, we can prove that G is generated by both G alpha as well as G minus alpha. Okay. So, in particularly this G beta for beta p plus, you can claim that this will be inside your subalgebra generated by G alpha alpha in pi. So, which you can prove that it is generated by x alpha alpha coming from pi. So, now using Jacobi identity, since this is lies inside this subalgebra generated by x alpha alpha in pi. So, this can be actually x beta can be written as Lie product of this form. Okay. This is called right normed Lie word, right normed Lie word formed from this x alphas. So, now you can see that, so this bracket must be non-zero as well as any given any I, the bracket must be non-zero. So, that means this beta is first of all alpha 1 plus etcetera plus alpha t, and alpha t and alpha t plus alpha t minus 1, all of them must be roots, there is no other option. This is in phi plus, this is in phi plus and so on, alpha I plus etcetera plus alpha t, that is also should be in phi plus, because this sum corresponds to taking bracket up to I. Okay, because the successive bracket should be non-zero because x beta is non-zero. So, this is the Lie algebra interpretation of the same result, but in the root system case it is not that hard to prove, but this also means something in Lie algebras, that is what I wanted to say. Okay, this is about some particular root spaces or the root vectors generating G, that is what it reflects. Okay, let us get back. So, this is the lemma that I left it as exercise before, I am going to prove it now. So, this is about simple reflections. So, you start with alpha inside your pi, then S alpha of phi plus difference alpha. So, that is permuted by S alpha. So, that means this is mapped to phi plus difference alpha. So, how one verify this? This is easy. You start with beta, which is in phi plus difference alpha. So, that means beta is not equal to alpha. So, beta you write it as summation k gamma gamma, where gamma coming from pi. Okay. Now, you know that this k gammas they are all coming from Z plus, because this beta is in phi plus. So, now beta is not proportional to alpha. So, again therefore, there exists gamma inside your pi which is different from alpha such that k gamma is positive. Okay. So, but the coefficient if you look at on S alpha of beta. So, S alpha of beta is nothing but beta minus 2 beta alpha divided by alpha alpha alpha. So, that means in S alpha of beta only the coefficient of alpha will be changed. So, that means this k gamma is unaltered. So, that implies that the coefficient of gamma in S alpha beta is still k gamma which is positive. That forces that S alpha beta must be positive because all other coefficients also must be non-negative. So, since S alpha of beta is not equal to alpha because beta is not multiple of alpha. So, that implies that S alpha of phi plus difference alpha is exactly equal to phi plus difference alpha. Note that S alpha of alpha is minus alpha. So, this is the only element that is sent to negative by alpha inside positive roots. Okay. So, in particularly as a corollary this is something I worked out already. If you set delta to be of some of these positive roots, so then it is clear that S alpha of delta must be exactly delta minus alpha. So, this is a simple computation that one can easily do. So, now we prove this another result which we left it as exercise. So, this we call it lemma C. So, what it says okay, to prove our result which is about the expression if you write sigma as product of simple reflections such that the number of reflections that are involved in that expression is as small as possible. So, this is the result that we actually left it as exercise. If you take sigma to be S alpha 1 etcetera S alpha t, where S alpha I coming from your alpha i's are coming from your pi and t is as small as possible. So, then we concluded that this sigma of alpha t that must be negative. So, this is the exercise that I left. So, to prove that we need some important observation. So, let us make that observation. So, you take this alpha 1 etcetera alpha t which is coming from pi, okay, and you assume that these are all not necessarily distinct. This is not necessarily distinct. So, you write this S I to be S alpha I. So, then if you know that this S1 etcetera S t minus 1 applied on alpha t is negative. So, then you can prove that there exists S 1 less than or equal to S less than t such that this S1 etcetera St is exactly equal to S1 etcetera S. So, maybe we will call it A 1 less than or equal to A less than t such that S1 etcetera St is same as S1 etcetera Sa minus 1 times Sa plus 1 etcetera St minus 1. So, what it says basically in this expression S1 etcetera St, S1 etcetera Sa A minus 1 A Sa plus 1 etcetera St is there, t minus 1 St. So, we will be able to remove these two reflections in the expressions of product of Si. So, that is what it says. Okay. So, this is called what is called deletion condition. Okay. This deletion condition actually plays an important role if we think about this Weyl group. Okay. So, basically one can prove that, maybe we will do it during the one of the problem solving session. Okay. So, this is called this lemma D, lemma C is called deletion condition. Okay. So, here is the remark, lemma C is called deletion property or deletion condition for the Weyl group of W, and this deletion property will imply W is a Coxeter group. Okay. So, Coxeter groups are groups that are actually generated by reflections. So, it is abstractly defined group. So, let us not get into the definitions now. Okay. So, later in one of the problem solving session I will actually prove this deletion properties indeed gives us W being Coxeter group, which is not very important for this course, that is why I do not want to do it. But what it says, whenever you have these condition that S1 etcetera St minus 1 applied on alpha t, if that is negative, then we will be able to delete one element in the expression in the middle and this last reflection St. Okay. That means, this if we take this sigma which is product S1 etcetera St, then this t is not indeed smallest possible. Okay. So, if sigma equal to S1 etcetera St and this S1 etcetera St minus 1 of alpha t is negative. So, then that implies that sigma can be written as product S1 etcetera SA minus 1, SA plus 1 etcetera ST minus 1. You can see that if you define the length to be the minimal t such that sigma equal to S1 etcetera ST, then the length of this sigma actually goes down by 2. Okay. So, we will talk about length later, let us not worry about now. So, let us prove this lemma C, and then as an application we will also get this exercise. Okay. So, how to prove this? So, all we have is, so this alpha 1 etcetera alpha t, they are all simple roots, not necessarily distinct roots. Okay. We have also set this Si to be S sigma, sorry, S alpha I. So, what is given? Given is S1 etcetera St minus 1 alpha of t, this is negative. Okay. So, what we do, we take beta I. So, this is by definition you take it to be Si plus 1 etcetera St minus 1 applied on alpha t, and this is defined for I from 0 to t minus 2. Note that beta of t minus 1 by definition it is just alpha t. So, this is the convention that we make. So, now you can see that beta of 0. So, that is going to be S1 etcetera St minus 1 applied on alpha t, this is negative, and what is beta t minus 1 which is the starting point. So, that is positive. So, that means if you go from beta t minus 1 to beta 0, it goes from positive to negative. So, in every step if you go down, so beta t minus 1 is positive, beta t minus 1 2 let us say it is positive and so on. So, at some point, so there will be a index A. So, there exists index A which is lies between this 0, not exactly 0, is between 1 and t minus 2 such that for which there exists index A for which beta S will be positive, because you are going down by beta t minus 1, beta t minus 2 etcetera beta A. So, beta A is positive, but when you go down beta A minus 1, okay, so that is negative, let us say. So, this beta is positive, but beta A minus 1 is negative. But what is beta A? Okay. So, you can see that so this beta A is positive, and what is beta A minus 1? So, beta A minus 1 is nothing but S I plus 1, that is A applied on just beta of A, and this is negative. So, beta A is positive and SA beta A is negative, but you already know that SA being simple reflection. So, SA maps phi plus difference alpha A to phi plus difference alpha A. So, that means this beta A forced to be alpha A, because beta A is being positive and it sent to negative. So, that forces beta A to be alpha A. So, now in particularly we can see that, so recall for any sigma, okay, for any sigma in W, we know that sigma S alpha sigma inverse is nothing but S of sigma of alpha. So, this is already there. So, that means, so if you apply this sigma A plus 1 etcetera sigma t minus 1 on this sigma t, okay. So, I am mixing sigma and S. So, let us go back to S. So, this is S A plus 1 S t minus 1 applied on this S t, and then you take the conjugation S t minus 1 etcetera S A plus 1. So, then you can see that this is going to be exactly equal to S of, so this is sigma, this is sigma inverse. So, this is going to be sigma of alpha t, okay. But this is exactly equal to, so if you go back to your sigma A, so that is okay S of A, which is S sigma of A. So, you can see that, sorry, where are we? So, we proved that beta of A is must be alpha of A, okay. So, that means beta of A minus 1 is S A of alpha of A, which is minus alpha of A. So, what is beta of A? So, beta of A is exactly equal to S A plus 1 etcetera S A plus 1 etcetera S t minus 1 of alpha of t, okay. So, that means beta of A is exactly sigma applied on alpha of t. So, which is exactly alpha of A, okay. So, that is what it says. So, now if you combine them together, you can see that this S sigma of alpha t is exactly S A, okay. So, now if you substitute it back this equation, that is S A plus 1 etcetera S t minus 1 S t minus 1 etcetera S A plus 1 is exactly equal to S A. If you substitute back inside your S 1 etcetera S t, for example, this can be rewritten as S A plus 1 etcetera ST minus 1 ST is exactly equal to SA, SA plus 1 etcetera ST minus 1. So, you can replace this by this in S1 etcetera ST. So, then we get S1 etcetera ST equal to S1 etcetera SA, SA plus 1 etcetera ST minus 1 ST. So, this is what we want to replace. You can see that this is exactly S1 etcetera SA, SA, SA plus 1 etcetera ST minus 1, which is exactly SA, SA will be square will be identity. So, then that implies this is exactly S1 etcetera SA minus 1, SA plus 1 etcetera ST minus 1. So, this proves that we can remove that index SA. So, S1 etcetera ST is same as S1 etcetera SA minus 1, SA plus 1 etcetera ST minus 1. So, the deletion property is satisfied by Weyl group, that is what it says. So, now let us prove that exercise, that is we promised. Okay, let us write sigma equal to S1 etcetera ST, and where this SI's are S alpha i's, where alpha is coming from pi, take t to be minimal possible. Okay. So, now what we want to prove? We want to prove that sigma of alpha t, that must be negative. Okay. So, what happens if it is positive? So, let us look at this sigma of alpha t. Okay. So, if we take the sigma of alpha t, you can see that this is exactly equal to S1 etcetera ST minus 1 ST alpha of t, but ST of alpha t is nothing but minus alpha t. So, then it gives us S1 etcetera ST minus 1 of minus alpha t. So, this is exactly equal to minus S1 etcetera ST minus 1 of alpha t. Now, suppose this is negative, then that forces this sigma of alpha t is positive. Okay. So, sigma of alpha t is negative if and only if S1 etcetera ST minus 1 of alpha t is positive. But you can see that if S1 etcetera ST of minus 1 of alpha t is negative, then from the deletion property we will be able to remove some index A. So, that is what this deletion property tells us. So, that means since t is as minimal as possible, we will not be able to remove any index SA from this product expression S1 etcetera ST. So, that forces that this S1 etcetera STF minus 1 of alpha t must be positive, and that forces that the sigma alpha t is negative. So, that proves what we actually promised to prove. Okay. So, let me just summarize what we have done so far, and then I will stop. So, here is the summary. So, summary about set of bases and so on. So, we started with the root system phi. We defined what is called base. Okay. So, we proved that any basis, okay, the set of bases of phi are given by pi of gamma, where gamma comes from regular, okay, gamma just regular. Okay. And we also proved that pi of gamma equal to pi of gamma dash if and only if phi plus of gamma is exactly equal to phi plus of gamma dash if and only if the chamber defined by gamma is same as the chamber defined by gamma dash. So, these are all the things that we proved, and then we proved that the Weyl group acts simply transitively on the set of bases. Equivalently, it acts simply transitively on the set of positive roots as well as the set of chambers. Okay. So, that means given any simple roots, okay. So, pi dash, so they are bases, let us say there exists unique w in w such that w of pi dash equal to pi. So, this is what we have proved so far. On the way we also proved that if we take w pi union w in capital W, that must be exactly phi. So, this is also something we proved. That means, any root must be W conjugate to a simple root. Okay. So, these are all the things that we have proved so far, and then we also understood some basic properties of the simple roots. So, that is what I did it today. Okay, I will stop here and I will continue with actually classification of root systems. For that purpose, we need to write given root system as direct sum of irreducible root systems. So, we will see in the next class how to do those things. Okay, I will stop. Thanks.